I hope you noticed some interesting patterns in your lab. For one, you probably noticed that as the temperature of your object increased, the color of the object changed, which is a little, maybe expected, but you probably didn't expect that the hotter the object was, it actually became more yellow and eventually more blue, which is a little bit weird. And so we can think of stars as black body radiators. They aren't perfect. They don't perfectly emit all of the energy, but they're close enough that they work really well. And you probably saw this in your lab. And you probably noticed that as the temperature of the object increased, its peak of its radiation actually shifted to smaller and smaller wavelengths. So here we're peaking in the infrared, here we're peaking in the green, here we're peaking in the ultraviolet. And so this interesting thing is happening, and you're noticing this pattern. And so we can look at different objects and really understand the energy that they put out based on this black body radiation and something that governs it called Wien's law, or Wien's law, if you want to sound fancy in German, and I think correct. So looking at that, and looking at that simulation you did, we see that stars all are giving out visible light. So no matter what color a star is, it's giving off some visible light. But we can see that the 15,000 Kelvin star, if we look at how much visible light it's giving out, I have a little zoom in, you can see that it's giving out more blue and purple light, which purple technically, anyway, more blue light than red light. And so that star ultimately is going to look blue to our eyes. The 5800 Kelvin star is peaking in the green-yellow region, so it's going to look yellow or even white to our eyes, especially if it's peaking in that green region. And then the cooler star, 3000 Kelvin star, is going to look red because, again, it's giving off more red visible light than blue or green visible light. And so we get more of that red receptor, that red cone inside of our eyeball, telling us that there's light there, which tells your brain, hey, that thing's red. Another interesting thing about black body radiation is that you can model pretty much any object that has a temperature using a black body curve. So these are all called black body curves. They describe the perfect radiation emitted by an object that is a black body radiator. When we were looking earlier at actual light curves from stars, they were a lot more bumpy. And that's, again, like I mentioned, they're not perfect black bodies, but they work really well. But the cool thing about Wien's law and black bodies is that you can use them to model any object. So for example, you have a temperature of about 310 Kelvin. And so you give off electromagnetic radiation. Did you know that? Isn't that cool? Can you guess which part of the electromagnetic spectrum this is? So it's 10 to the 4 nanometers is about where the peak is. And so this is actually the infrared radiation. That's why we can see people with infrared light, because we glow in the infrared. So, like I was saying, where the star's peak is really affects the color that we perceive. But it not only tells us the color, right? Color is cool and all, it's pretty, but just by knowing where the peak is, you can actually then determine the temperature of the star. And so I talked a little bit about this earlier, that using the sun as a black body isn't exactly perfect and that their energy is getting spread around, but thermodynamically we're okay with it being a black body, and I'm gonna not get into any more detail there. But what I do want to really highlight is the pattern that you found in your lab. So you found that when you looked at the temperature of your object versus its peak wavelength of light that it was giving off, the wavelength with the maximum intensity, you found an inverse pattern. So I'm going to go back here. As the temperature got bigger, the peak became smaller. Not just smaller in height, which it also becomes smaller in height, but smaller in wavelength. So our 10,000 Kelvin has a peak at like, I don't know, 300 nanometers. And then our 6,000 Kelvin, about 550 nanometers. Then our 3,000 Kelvin, that cooler star that looks red, has a peak of 1,000 nanometers. So as the star's temperature decreases, its wavelength increases. So there's an inverse pattern between them. And what that means mathematically is that the two things multiplied together, the maximum wavelength, that peak wavelength, times the temperature, is going to equal a constant. And the constant that it equals is 2.9 times 10 to the minus 3 millikelvin. Eesh. No, that's not true, Ms. Getz. You're making things up. That's not an M for milli, because if it were an M for milli, it would be right next to the Kelvin. So that's an M for meters, which would make sense because we have wavelength in meters, and then we have temperature in Kelvin. There we go. So we have this handy equation. It is in your IB packet. I don't remember what page it's on, but I'll just find out and let you know right now. So it is the last page, actually, very handy. Page 14. You have this equation in your packet. You don't have to memorize it. Again, don't memorize equations in physics. But I do have a couple of sample problems for you because I also have some IB problems you can work on as our last activity this week. So here we have this first example problem. We have a star with a surface temperature of 10,000 Kelvin. At what wavelength will this star emit most of its light? And what wavelength region is this? Ooh, good question. Okay, so I'm going to start out by going ahead and writing down all of my knowns in the equation. I've got this 10,000 Kelvin surface temperature, so that's 10,000 Kelvin. My temperature is already in Kelvin. It's pretty unlikely in astronomy that you'd have to do any unit conversions because, again, we're not measuring the temperatures of stars with thermometers. So then, do I have anything else? Oh, I want to know what the wavelength is. Wavelength max equals question mark. And that looks like it's it. So I'm going to go ahead and write down my equation that the wavelength max times the temperature is equal to 2.9 times 10 to the minus 3 meter Kelvin. Again, that's an M for meter. And I want to solve for the wavelength. So that means I'm going to divide the equation by temperature on both sides. Algebra is still useful and will remain useful. So we have 2.9 times 10 to the minus 3 meter Kelvin divided by the temperature. And then I'm going to go ahead and plug in my actual numbers for this problem. So I have 2.9 times 10 to the minus 3 meter Kelvin divided by 10,000 Kelvin. Notice that the Kelvin are going to cancel out and I'm going to get an answer that is in units of meters. And I know that I'm going to have, let's just not even bother using a calculator. So this is actually the same thing as saying 10 to the 4th on the denominator. So the way you do denominators is you take the 10 to the minus 3 minus 4, so this will be 10 to the minus 7. So it's 2.9 times 10 to the minus 7 meters. And then I have to go ahead and say, answer that second part of the question, what wavelength region is this? What part of the electromagnetic spectrum? Well, just based off of the lab that we already did and the example stars that I've looked at, I'm pretty sure that this is going to be in the ultraviolet region. It's 290 nanometers, so it's clearly not visible light. Visible light only goes down to like, I don't know, 400-ish, 430. And so this is in the ultraviolet region on the electromagnetic spectrum. And so for our eyeballs, it would look blue. Let's try another one. Oh no, come back. So in this other one, our sun gives off most of its light at the yellow portion of the electromagnetic spectrum. at an average wavelength of 510 nanometers. Use Wien's law to compute the average surface temperature of the sun. So here again, I'm going to write down my knowns. I want to know what the temperature is. I know lambda max is equal to 510 nanometers. I also happen to know that 510 nanometers just means 510 times 10 to the minus 9, because nanometers is 10 to the minus 9. Oops, it's no longer nanometers, it's just meters. And then if I want to know the temperature, again, I'm going to use the exact same relationship, 2.9 times 10 to the minus 3 meter Kelvin divided by my wavelength. So 2.9 times 10 to the minus 3 meter Kelvin divided by 510 times 10 to the minus 9 meters. I am running out of time, and 2.9 510 to the minus 9, go. Woo, that's a hot star. Or is it? 5,686 Kelvin. Is that a hot star? What do you guys think? About 5,600 Kelvin? Not so much. It's actually a pretty cool star, or maybe an average temperature star. Our sun is essentially an average star. So we have done a lot of thinking about what we can tell from the color of the star. So next week, we're going to start thinking about using this black body model and Wien's law to really look at the total energy output, or the luminosity of a star. And we'll get a little bit deeper into some calculations before we can put both of these calculations that we're doing together to get a fuller picture of the different types of stars that are out there and what their lives are like. Because actually, everything astronomers know about stars and stellar lifetime and stellar death and the different types, all of that stuff is information that we have learned by looking at the light from the stars. We have taken the light, spread it out using that spectroscope tool that uses a diffraction grating to spread out the star's light, and really examined it and looked at these regions where there is light missing, or where we have a higher peak of light, where we're seeing those emission spectra. And that's how astronomers know all of this stuff. And so we're going to dig a lot more into that next week. Hope you're doing okay. Miss seeing you all in class. Take care.